So this is the part of the chapter which will be most linked to numericals and problem solvings, and this is where we'll try to attempt and solve as many problems as possible as well to understand the concept of conditions of equilibrium. Now I must tell you that we have studied conditions for, there are two conditions for equilibrium, and basically we say that there are two types of equilibrium, and you have studied both of them already. You have seen them in previous videos as well. What we are doing here is just consolidating that information into one simple lecture, because that actually helps us solve many of the problems when we use both of those conditions together to solve problems. So the first one actually has to do with that is basically the condition that basically helps this object to stay stationary. That is what the first condition is actually doing. It is helping the object to not move and stay put in its place. And the second condition is actually doing what? It's actually helping the object to not rotate. And to prevent rotation, that second condition needs to be fulfilled. So the first condition, which is necessary for the object to be stationary or to stay at rest and not go anywhere, to not move, basically not to change position, actually comes from Newton's first law, which we have already studied. It actually has to do with Newton's first law. Now you have already studied this. So the condition is pretty simple. The condition is that if you are to stay stationary, then sum of forces in one direction must be equal to sum of forces in the opposite direction. This is what the first condition is, and what it's actually saying is that if I give you an object, and let's say this is the force F1, this is another force acting on it, let's call this F2, and this is another force acting on it, F3. If this object is to stay stationary and not go anywhere, not move anywhere, then it must satisfy the above condition, which says that sum of forces in one direction must be equal to the sum of forces in the opposite direction. And for this situation, it's basically that the upward forces, if you add them together, should be equal to the downward forces. So what we are actually saying is that F1 plus F2 should be equal to F3. This condition must be fulfilled if the object is not to move. Now, this condition actually appears in a different wording as well. So let's learn that as well, because you might again see it in exams written in a different way. So you should know all the different terminologies. So you might also see this. The resultant force must be 0. And this statement, or the statement which is written above, are basically saying the same thing. If you look at the object, the forces on it, F1, F2 and F3, when you find their resultant, since the above forces acting upwards and the force acting downwards are in opposite direction, you will have to subtract them. So you can also write it like this. You could also say that F1 plus F2 minus F3 should actually give you 0 Newton as your answer. which is also the same thing. It's basically just the rearranged form of the above equation. Now, the second condition actually has to be fulfilled if the object is to not rotate. So what we are basically saying is that if this is a prism and there is a rod which is placed on it, so in order for, and there are, let's say, a bunch of weights acting, let's call this F1 and let's call this F2, and you are given distances from the pivot, let's call this D1 and let's call this D2. Then what we are really saying is that the moments that are produced by each of these forces, the anti-clockwise moments and the anti-clockwise the clockwise and the anti-clockwise moments, sorry, they must be equal to each other. So in order for the object to not rotate and in order for it to be in a rotational equilibrium, what we are actually going to write here is the principle of moments, which was actually what the last video was about. So the principle of moments is basically the second condition of equilibrium. So that would be sum of anti-clockwise moments about a point must be equal to the sum of clockwise moments about the same point. So if you remember, this is exactly what we wrote down in the previous class as well, that clockwise and anti-clockwise moments must be equal. But just like the first condition, this might also appear in a different manner, and for that you will write the statement: the resultant moment, or they might also use the word torque, the resultant torque must be 0. But this statement and the statement above is exactly the same thing, and what they're saying is that if you sum up all the clockwise moments and all the anti-clockwise moments, and you take anti-clockwise as positive, let's say, and you take the clockwise moments as negative, and then you add them together, obviously what you're gonna get is 0. So that is what the second condition is saying. So just like the first condition helps you make an equation, the second condition will also help you come up with an equation, and once you form an equation, that is what actually helps you solve many of the problems. So the equation for moments might actually look like this. For the above beam, it would be, let's say, clockwise moments, which will be F2 multiplied by D2 equal to anti-clockwise moment, which will be F1 multiplied by D1. And if anything is unknown in a problem, you can find it out using the equation which we have just formed.